it just kick? Okay. Let's see. Maybe close it down and come back in. Oh, there you go. Add. Okay. Okay. As soon as you guys can hear me on the chat, I'll get started. Oh, looks like the numbers dropped, so everybody must be kicked to the ad. All right. What's that? Oh, well. Nope. Okay. You can turn that down now. Okay, great. All right, so looks like people are getting in here. We got about 30 people in. All right, cool. Looks like everything's coming through okay. Good, good, good. We'll just give it just a minute or two here. So this particular live stream, it is kind of equipment heavy. So I've got a table full of craziness going on. I've got a document camera over here. I've got wires. I've got resistors. Yeah, I'm surrounded. So I'm probably at some point going to press a button or hit something on a pad or something, and it's going to send everything kicked off. See, we've got people in the comments here. Looks like everybody's coming in, can hear everything. All right, cool. Yeah, looks like we are just about good to go. Thanks for coming to the live stream, guys. I realized today that if you just took a frame from each one of the live streams, it would look like my head's turning into a chia pet. Just kind of more and I imagine everybody out there right now has a similar sort of haircut going on. Start going for the party in the back here soon. Let's see. All right, so this morning what we're going to do is cover a few things with basic electronics. I've got some stuff that was pulled out of a current class that is part of the applications class where you build your own stuff. So this section that I've pulled out is just kind of the basic electronics review section. Let's see, there is, just looking at the comments here. Okay, cool. Looks like more people are coming in. All right, good. Everybody's popping in. All right, so first what we're going to do is we'll do some basic electronics review, and like I said, this is kind of the part of a class. And then we're going to slide into a little lab that's a part of that class that just kind of shows how to use a breadboard. So we've got, I put out on the website a parts list that you could have chosen to get. I think it's about $16, $17 worth of parts. It's a breadboard, resistors, LEDs. So if you've got some of that already hanging around, you can follow along, or you can just watch as I go through it. That's fine. Also, there's some written materials on the website. So if you need the link, it should be in the description of this video. That will take you over to the website where you can download a zip file. And there's the SHA-1 hash there if you're a little paranoid about being in the right file. So go over there, grab that, download it, and there'll be a worksheet, 3 PDFs, and I think something else. I can't quite remember. Those PDFs are the data sheets for some of the components we're going to be looking at. So the way this is going to work is first we're kind of going to go over basic electronics review. I know a lot of you have had basic electronics at some point in your career. but it never hurts to kind of knock the cobwebs off. And what's killing me is that I usually do this in a very interactive way where I'm asking questions, people are responding, but with the egregious delay we have in the live stream, we'll just kind of go over that. The next thing we'll do is look at the breadboard itself and just how it's constructed and how you put components in it and things to look out for when you're messing with the breadboard so you don't run into any trouble. After that, we'll go through the student worksheet where we will look at kind of a situation where we're going to be taking and putting LEDs into a breadboard and figure out how is it that you pick the right resistor for the LED that you're going to use. And so we'll just kind of make a really simple circuit. In the end, we'll end up with a couple of LEDs and a couple of resistors in a circuit. Then we're going to take that circuit and we're going to go into KiCad. So that's another thing you're going to find on the website is a link to download KiCad. Some people pronounce it KiCad. Probably the right people pronounce it KiCad, and I'm pronouncing it wrong. It's just hard to give up on a really bad habit. But download that program, install it. There's installation procedures there for Linux or Windows or Mac, I believe. A host of operating systems. So just find the one that matches your system, download it, install it, and what we'll do is take that really simple schematic that we're going to make and transfer it over to KiCad, and we're going to make a schematic. We're going to put parts on that schematic. We're going to then associate every symbol in that schematic to an actual part. Take those parts, move it over to a secondary program within the KiCad suite called PCB New, and then we'll take those components, put it on that program, and arrange it. And actually, at the end of this, you should be able to take the files that it generates and go out and purchase you a PCB that will be generated by what you've done in class. So it's going to be a really simple circuit. There's not going to be a lot involved with putting it together, but we're just going to kind of keep it simple in order so I can show you kind of the basic functionality of that program. If there's kind of demand to learn more about that program, we'll be taking questions, and if it looks like there's a bunch of questions going a particular way or not going to have time to cover it all, we'll just make another class covering KiCad because there's a lot of stuff we might not be able to get into. Such as making your own parts or how do you bring in custom logos and things like that. So there's a lot of different things you can do in that. So we might make that subsequent classes if there's any interest in it. So that's kind of the plan for today. Obviously, my plans are usually more than we can cover, so this might turn into 2 classes. I'm not really sure yet, but we'll soon find out. It's good to see everybody here. Looks like we got kind of hitting our average, what we usually have, somewhere around, let's see, about 50 people or so that's cool. I'm going to get my fat head out of the way here and throw it down in the corner, and if my fat head gets in the way, just let me know. I'll move it around on the screen there. So we're going to start with the basic electronics review. I'm going fancy today. I've got a pen here that I can kind of write on the screen, so that's fun. So we'll play around with that and see how it goes. All right, so first thing is I want you to kind of, as these pop up, just try to, in your head, see if you can remember what these symbols are. We got something that looks like this, little like polarity sensitive like plates. We got a squiggly line. I got another thing that looks sort of like, 2 things mashing together like 2 pistons. And then we've got a little triangle symbol with some arrows pointed out. So the question are, name each one of these symbols, right? So these are all common symbols that you'll see in many schematics. So if you're unfamiliar with schematics or you're trying to reach back in your brain and figure out where these things come from, A would be a battery. So some people say a symbol comes from like different plates in a battery or just kind of the different elements. Got a negative side and a positive side, and at the positive side you have a positive polarity, negative side, of course, negative polarity. And typically when we're talking about current flowing, and we'll get into that in a second, actually I'll save that for later. But yeah, so this is what you see as a battery symbol. B is a resistor. So resistors typically are used to kind of control current flow, and we'll get into what that is a little bit later. C is a capacitor. Capacitor, Brandy just gave the fist pump over here because she just she's excited she remembered that one. Brandy, by the way, sits through a lot of the classes that I teach, and some she's taken and some she hasn't. And so this is one that I don't think you've taken this one, have you?
No, but I see these all the time on our schematic.
Oh yeah, so she hasn't taken this one, but she sees these all the time, and she started to remember them. But yeah, so this is a capacitor. It stores energy. You can charge these up really quickly and discharge them just as quickly. They're really fun to make tasers out of. I've got one here. Maybe I'll break that out later and show you what a homemade taser looks like. Yeah, it'll rattle your teeth. It'll also put heavy burn marks in metal door handles, but I'll show that off later. Then D is an LED. Now this looks like some of you might be thinking like, oh, that's a diode. You're right, but an LED is a diode, light emitting diode. The reason I know it's an LED and not just a diode is because of the arrows. That indicates that there is light coming out of it. So that is an LED. Let's see. So this thing, how much voltage does one of these provide? If you look really closely, and if you have your screen pushed all the way up, you'll notice it provides 1.5 volts. It says right there on the battery. So a lot of these batteries, AA, AAA, C batteries, they all provide 1.5 volts. It's just the amount of capacity they have to provide that, right? So, obviously a smaller battery is going to have a smaller capacity to be able to supply any sort of power. But it's good to know, like we call these square batteries like this, 9-volt batteries, just because, yeah, they're 9-volt, right? But sometimes we forget, like, just how much you can get out of a small battery. So with that, though, if I had 4 AA batteries, so just like the ones I showed previously, and needed to create a 6-volt voltage source, how would I do it? So I'll let you think about that for just a second. So kind of the way that you want to think about it is, what arrangement. So, you can take these batteries and you can arrange them and connect them in different ways, and you can produce different things. So one of the ways you can do it is you can stack them all together side by side. We call that stacking them in parallel. And if you do that, and you have all of these positives hooked together and all these negatives hooked together, what happens is you don't increase the voltage any. What happens is you increase the capacity. So if you had one battery and you stack it with another battery, what you're then going to have in this configuration is a giant battery that's going to last twice as long. In this case, you've got 4 of them, so it's going to last 4 times as long. So as long as your application only needs 1.5 volts, you can take and stack 4 of these side by side, and you're going to get a longer capacity. If you wanted this thing to last longer and longer, you just keep packing them in parallel. However, if you need to reach a certain voltage, what you do is you put them in series, so front to back. What you'll notice is in a lot of applications, like if you take apart just about anything and start looking at it, especially like a remote control or something, a lot of these things require 3 volts or 6 volts, but mostly you think around 3 volts, and those batteries will be stacked in series is what they call it. So that's when you get front to back. And every time you stack something in series, when it comes to batteries, you increase the amount of voltage that it's able to provide. So one of the things you can do, if you've never seen it done, is you can take these 9-volt batteries and they've got a tiny end and a fat end on the top, and you can take the tiny end of one battery and stick it in the fat end of the other. And what you'll end up is, if you keep stacking them like that, is you'll just keep adding 9 volts to 9 volts to 9 volts, and you can end up with a huge bank of very high voltage battery source, to which you could then connect one of the aforementioned capacitors and shock the ever-loving mess out of someone. So somebody just said, are you going to teach embedded 2 in the future? I don't know. We'll think about that. I'll have to write that down and see if there's anything we can do with that. Okay, so what is the value of the resistor below? Excuse me. Now, some of you kind of remember you had different levels of resistance that are different. Know that these different colors mean different things. So what's the value of this thing? So I know there's some acronyms out there and some different mnemonics or different things to remember what this does, but can you remember what this one is? So this is a 4-band resistor. So there's a difference between a 4-band resistor and a 5-band resistor as to the way you calculate what the thing's worth. So in this case, a brown is a 1, black is a 0, and this red one means 10, because red is usually red means 2, but since it's the 3rd band in this capacitor, it's going to be 10 to the second. Okay, so that means you got 10 times 10 to the second equals, okay, yep, somebody just popped it up there, 10K, that's correct. So 10,000 ohms. And you have to forgive me with my sloppiness with this pen. I don't use it this often. But yeah, so you got 10 times 10 to the second is 10,000 ohms. And so there are different ways to calculate. Now this last one down here, that is a percentage value of how accurate it is. So you can have a 1%er, a 5%er, a 10%er. And so typically I am very good at this, especially on a 4-band resistor. I'm really good at it because in college I was a research assistant, and one of my jobs was to keep the lab clean and sort resistors back to where they belong. So I got decent at it there. And then I worked at a place one day when I decided to try and gather all the resistors in the facility and put them together, and was successful in that. But in the process, everyone found out that I was doing that and kept bringing me more resistors, so I sorted thousands of these things, and now it's burned into my brain. But yeah, so you can usually look at a resistor and tell just what the value is just by looking at it. Now, the way this kind of works out is there's this color code. Like I said, I'm really good at the 4-band stuff. The 5-band stuff, I'm okay at it, but it's kind of like reading music to me. I just kind of have to sit there and stare at it for a while before I can remember that, oh, it doesn't use the same system. The multiplier is on the different band. So it's hard for me to just I'm intuitive with this one. I'm not with this one, and I'm terrible with the 6-color band. I don't even see many 6-color bands. But the tolerance down here, like before, we had a gold band, so that'd be a 5% tolerance. Values I'm good at, tolerances I'm kind of terrible at remembering, but there's a way to kind of tell with these when you're looking at them. All right, complete the following. Voltage equals current times resistance. And if you've seen this before, you've probably seen it written as V equals IR. You might have also seen it written E equals, I believe, IR. E and V both stands for voltage. This is known as Ohm's Law, if this is the first time you've ever seen it. And so it's just a way that we can relate voltage, current, and resistance. And just kind of the interplay in between those. So there's always, if you can calculate 2 of these, you can always come out with a third. Now, it brings up a couple of good questions when we start talking about Ohm's Law, that a lot of people memorize Ohm's Law, but then don't understand what we're actually referring to. So what is voltage, right? So this one this one kind of messes with people sometimes. It's just asking, like, well, what is voltage, right? So voltage is something we call potential difference, right? Good way to think about it is on the terminal of a battery, you have a buildup of a lot of electrons on one of these terminals. On the other terminal, you have a dearth or just a lack of electrons. And so you've got this great, stacked full of potential on one side with not so much potential on the other. And as soon as you bridge between the two, you're going to make those electrons start flowing from one side to the other, because just in nature, right? If you've got I've got a room full of hot air and a room full of cold air, and I open the door in between them, what they're going to want to do is mix, and that hot air is going to want to diffuse throughout until it finds some kind of balance. Well, the same thing happens with a battery. You've got a build up on one side and a kind of a lack on the other, and it's going to try to find a pathway to get over to that other terminal. And if you supply that, it's going to allow those electrons to run. So that's what voltage is. It's just that build up in between the two. It's that potential difference from one side having a lot of charge and the other side not having so much charge. Which brings us to the next question: is what is current? So what we said is, if you've got a lot of charge on one terminal and you don't have that much on the other terminal, and when you stick like a wire or something in between it, you're going to get that flow. Well, that flow, that rate of that flow going from one side to the other, that is current, is the actual charge moving from one terminal to the next, the electron moving from one side to the other, and how much of that is going. Now, if you do take a wire and you stick it between these two terminal points, the question I always said, well, how much current will go across that wire? And I'd say it's all of it will. There will be a lot of current that will run across that wire, as much as the battery will allow. And that wire will get really hot, and it will either burn up the wire or burn up the battery, depending on how thick the wire is, because it gives a lot. But just so you know, like, current is that flow of electrons. All right, so now we get into the kind of the third element. So we talked about voltage, talked about current, we talk about resistors, right? So in what configuration are the resistors below? So what a resistor is something that you can put in that line, put in that wire, in order to slow that flow down, right? So typically they're made of all kind of different materials. Carbon is pretty common, some ceramic. There's a wire round resistor. There's all kind of different things, but what it does is it slows those electrons from getting from one path to another. It is a conductor that is intentionally tampered with to make the conductance much less. And it's down to a fine science, because now they're able to just tell exactly how much they want to slow that electron down, right? And so that's what a resistor does. This is a current control device, so that wire, when you stick it between the positive and negative terminal, doesn't get red hot. You're actually slowing it down so that it's able to control that current flow. So in this case, we've got three resistors. We got a battery here that supplies voltage. We got three resistors, and it says, in what configuration are the resistors pictured below? And so just like a battery, if you put these things end to end, we said that the battery would be in series if we put batteries end to end. Same thing with resistors. If you put a resistor end to end, we're saying we're putting the resistors in series. And so so one of the things about this, and I think I'll get into it, but I'll say it later, but that's commonly what you would call that. How would you determine the total resistance in the circuit? Now, just like batteries, when you stack them end to end, and they're batteries in series and you add them together, same thing with a resistor. So if you had 50 ohms on R1, 50 ohms on R2, and 50 ohms on R3, you stack these guys together, you're going to have 150 ohms total. Now, I always like to try to at least tell people people say, like, well, why are you telling me this? What good is it for me to know the total resistance of a circuit? Like, why don't I just use a 150 ohm resistor? Well, the reason you would use maybe something in series is because you don't have the values that you're looking for, right? So let's say you need a 150 ohm resistor, but you can't find one. So what you're going to end up doing is stacking what you've got together. It might be a 100 ohm resistor and a 50 ohm resistor, but you can put them in series and you can make 150 ohms. In college, we had to build a multimeter from some components that we had, And I was not on the main campus to do this lab. And so they had all the resistors that they needed. Well, in our little remote campus, we just had a few values we could pick from. And by the end of the day, we were taking resistors and putting them in series and in parallel, which we'll discuss in a second, and making the values that we needed. But the result was that we had two massive, two massive breadboards that were just full of junk on both sides. But it still got the job done. If both of these resistors are 50 ohms, what is the total resistance of this circuit? So what we've done is we've taken these resistors, and instead of having them in series, we're having them in parallel, so they're together. And so in this case, what's going to happen is current's going to be kind of split between the two, and they're both of the same value. And so you have some choices here. Do they remain? Does the total resistance of the circuit remain the same? Does it go up? Does it go up by a value of a couple? So what's going on? And so in parallel, what happens is these resistors actually decrease. So if you have a 50 ohm resistor and a 50 ohm resistor, you put them in parallel, you're going to decrease down to a 25 ohm resistance. Now there's a formula for that, right? So it's a kind of nasty formula, but you can take and you can do some algebra and figure out what this thing looks like. And so you can take 25 ohms and you can take these 25 ohms, you can put them together, you can use this formula and say R total, R1 and R2, so 25 ohms, so pretty much this value would be 25, this value would be 25, and the values past this you wouldn't use. And you'd get, 50 ohms in R1, 50 ohms in R2, and then get rid of the rest of this. And when you figure all this out, you end up with 25 ohms. The big thing is, a lot of times I don't go through and figure out what the exact value is going to be when you put two in parallel. Just looking at the comments real quick. But I intuitively, the main thing about when you're building circuits is kind of building this intuition on what things will do if you put them together, right? So if you put something that's 50 ohms in parallel with something with 50 ohms, just intuitively know that the result of that is going to be less than 50 ohms. In fact, it's probably going to be less than half the two values. And so, it's good to know all the formulas and stuff to be able to figure stuff out exactly. But when you're just kind of popping stuff down on a breadboard and you're trying to figure out like what's going to work and what's not, and all of a sudden you say, well, I need something that's I need a resistor that's less than 50 ohms, but the lowest one I got is 50 ohms, right? So what you can do is you can pop two of them in parallel on the board, and you know you're going to get something less than 50 ohms. And so, so that's kind of the thing with these two questions, with the series question and the parallel question. It's not so much to know the exact formula of what happens when you add these together or when you put these in parallel. The thing is to remember that in this configuration, things add together. In this configuration, things are less than the total of, that are less than, one of these components. So if you put two 50s together, it's going to be less than what you think. It's going to take and it's going to drop the resistance down. And so when you're looking at stuff, it's more about the intuition than it is about just trying to nail down the formula exactly. Yeah, so somebody said just like wiring up a car, stereo speakers for an amp. Yeah, so that's actually a really good comment there, Wesley, because I had a buddy that was, oh, are we losing connection? Are we good? Okay, yeah, looks like we're good. So I had a buddy that was wiring up speakers, and he had 8 ohm speakers, and he had some speaker selectors, and he was hooking in these speakers to his to an amplifier. And what he did is to try to save some space on his speaker panel is he started, actually he didn't have a speaker selector, that's right. He was just coming straight out the back of this amp tuner. And he stuck all of the speakers into that amp in parallel. So just, stacking one after another. So positive, 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 negative, 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 negative. And what happened is that 8 ohm speaker, after 2 speakers, turned into a 4 ohm speaker. After a third edition, turned into a 2 ohm speaker. After the fourth speaker, I think he added, finally the internal electrical protections of the amp popped and would not allow him to put any more speakers into the thing. It had a protection circuit, because what was happening is he was dropping the resistance of those speakers little by little by little, and it's pulling more and more current out of that device. And so he had to actually bring the whole thing in, and we took a look at it and found there was a reset button sequence push that you could take and then reset the protection circuit that was inside the amp. But yeah, like, you know, when you're wiring up stereo speakers for an amp, like this stuff comes into play. Pretty heavy. What is the current through the 3K resistor? So we can sit here and do the math, but generally to kind of figure out how to do this, all we're doing is we're going back to that Ohm's Law setup. So find my pen here. So if we've got V equals IR, which is the formula that Mr. Ohm found out for us, we go 9 volts equals I times R, which is our 3K, or we'd say 3,000 ohms. And so your I is going to be equal to the 9 volts divided by 3,000 ohms. And I believe that would be, let's see, what is that? 300 milliamps, I think. Let's do a quick, my math's not so good in my head. So yeah, so 9 divided by 3,000. Yeah, so this is going to be our 3, or you can say, well, you can say it 2 different ways. You can say 0.003 amps, or call it 3 milliamps. Okay. So another thing that's, when we're talking about intuition and trying to figure things out, another thing that is good to know is being intuitive about amperage. So current flow, like you hear a lot of people say, like, it's not the voltage that kills you, it's the current. Well, okay, sure, but one doesn't happen without the other. The thing with current is that I find that generally people who don't mess with electronics a lot don't understand how much a lot of current is, because there's a lot of misconception about that. So when I was in college, I was putting a circuit together, and we put a component in upside down, and I had the power supply select to 2 amps. And what that means is that power supply will not step in and cut you off of the current until it hits a 2 amp of current pull. And as we're sitting there, like, trying to put the circuit together, my buddy says, "I smell something," and started looking, and he's like, "I think something's wrong with this chip." And I put my finger on it, and it is just burning hot. In fact, it started burning the plastic on the development board we were using. It started to melt it down, and the professor came up and turned it off real quick, and he yelled at us and said that 2 amps could kill a man. But 2 amps didn't mean anything to me, because I was just starting out in this stuff. I didn't know what that meant. Well, there's some interesting stuff when you talk about amperage, right? So if you take just a few milliamps of current and you were to take and put it on electrodes across the human heart, you'd probably kill somebody. If you want to take and you got several amps, and you go up to let's just say this, if you go up to your wall socket and you touch the don't try this at home. You touch the elements on your wall socket. Well, you'll notice that you'll get a few. You'll get quite a push, right? And so that'll shake you up. And there's quite a bit of potential amperage going through that circuit. If you pull too much, it'll pull the breaker in your home system. And so trying to figure out, like, well, how much is a lot is kind of a relative thing. It's depending on where that amperage is applied to, and how it's applied, and what's applied. There's a lot of mystery in that. The main thing to know is that something like 3 milliamps, 10 milliamps, 100 milliamps, if you're just touching the two wires with your hands, a lot of times if something says it can, yeah, somebody just put 100 milliamps can hurt, or 10 milliamps can hurt, 100 milliamps can stop the heart. Yeah, and it all kind of depends on where. One thing you'll notice is the human body sometimes is kind of a poor conductor. And so it in respects to your skin. But if you pierce the skin, now you're just a big water bag, right? And that conducts water that conducts stuff a whole different way. So it just like anything, it kind of helps if I've got a circuit that's pulling. I'm messing with LEDs and resistors, and it's a live circuit. I'll pull components in and out of it all day long. DC current with just a few milliamps worth running through it, it doesn't bother me. I don't even feel it. But if I'm dealing with something out of the wall socket, all right, we're playing a different ball game, because I really don't want to be shocked for the ninth time. There's been I could tell a lot of stories about that. But anyway, just know that when you're trying to figure stuff out, right? V equals IR, 9 volts equal, just like the formula we had there. You can calculate, if you get two of these values, you can calculate the other one. All right, so anyway, question 12. If both of these resistors are equal in value and the voltage is 9 volts, what is the voltage across R1? So this goes into a realm of electronics called a voltage divider. So let's say there's a certain type of voltage that you're trying to acquire, that you need. One of the things you can do to get that voltage is to build a voltage divider. Let's see, did you, just reading through the comments here, I got, did you just call me a big water bag, Rue? I'm calling us all a big water bag, Roger. But over here we got this voltage divider. And so if you've got, the way it works is if you've got this, let's just say this is, like it says here, a 9 volt source. And both of these resistances are the same value. It doesn't matter if they're both 50 ohms, both 100 ohms, both 1,000 ohms. If they're both the same value, what will happen is that from this point to this point, if you take a multimeter, you will measure 4.5 volts. And from this point to this point, you're going to measure 4.5 volts. Because the way you divide voltage is always based on the ratio of the two resistors. It does not matter the value. If those are both 1 ohm resistors, you're going to split the voltage 4.5 volts on each way. However, that also goes another way, right? So if one of them is 2 times larger, so you got a 2 ohm resistor and a 1 ohm resistor, well, what's going to happen is you're going to have more voltage in that 2/3 ratio, right? So what will happen is you will have if this is 2 ohms and this is 1 ohm, you're going to have up here a 6 volt drop and down here a 3 volt drop because of that ratio, okay? So it all depends on that ratio. One more example, if this is let's say this is, what would be a good one? Say 10 ohms and this is 1 ohm, right? Then up here you're going to get, what's that going to be? Crap, yeah. This is going to be, well, in this part down here you're going to end up with like a 10% of the voltage, and up here you're going to end up with the rest of the voltage, 90% of the voltage up here, and so it's all about kind of this ratio game. And so there is a formula for this. If you wanted the formula, you're going to have the voltage source equals whatever resistor you're looking at. So R1 over R1 plus R2. But this is just a fancy way of saying it's all about the ratio, right? Or actually, I should say this is it, voltage source and the voltage across R1. So if you're looking for the voltage across R1, it's the voltage source times R1 over R1 plus R2. But the main thing to remember is just always remember ratios, okay? So if you got a voltage source, this is a certain value, this is a certain value. If these values are close to equal, then you're going to know that the voltage is nearly the same dropping across both of them. If they're out of whack, you know, if this is the larger one and this is the smaller one, there's going to be more of a voltage drop over here than there is over here. And that's what we're talking about, that kind of building that intuition up, right, about electronics. And instead of just knowing the formulas, is knowing intuitively kind of what they do. What voltage source, in this case, the voltage source is 9 volts. What is the voltage across R1? Interesting thing when you have things in parallel like this is, I had it shown to me this way. Well, how do you know how much is across R1 and across R2? Well, when you're looking at a circuit like this point right here is the very same as this point right here, is the very same as this point right here, because they're all connected by one wire. There's no difference between these 3 points. Likewise, down here, this point and this point and this point, these are all the same, and these are all the same. So if we look right here and we say this is between this point and this point on the battery is 9 volts, then the voltage across R1 is also 9 volts, and the voltage across R2 is also 9 volts, right? So no matter how many we stack in line with these, R1 will always have a potential difference from this point to this point at 9 volts. So so just kind of the takeaway on this one is, anytime you have a wire that, say, you know, like even this point to this point, right? All of this is the same. There's no difference between this point and this point. When I say, like, well, what's the voltage over R2? Well, these two are the same and these two are the same, so the voltage across R2 is 9 volts as well. So just kind of throw that in the back of your mind. All right. What is the major difference between these two types of capacitors? So we got one here that looks kind of like a can, and what are you laughing at? Oh, okay, all right. We got one here that kind of looks like a can, and we've got one here that looks like a blue disc. And so the question is, you know, what's the difference between these two? Well, this one's considered an electrolytic capacitor, and this one is just a normal capacitor. I'm not sure what this one's made of. It might be ceramic. It could be something else. But in this case, the major difference here is that one is polarity sensitive and the other one's not. So if you hook this capacitor up, generally with these canned electrolytic capacitors, you can have a larger capacitor value in a smaller size for a cheaper price. If you try to get one of these capacitors here, and I've done this in one of my products, I've got a 10 microfarad capacitor that's a ceramic capacitor, and the thing's huge. But a 10 microfarad in electrolytic is much smaller. But the thing is they are, the electrolytics are polarity sensitive. So the negative side, the part, the shorter leg, you always want to connect that to negative. The longer leg always goes to positive, and you'll also see a stripe on the back of the capacitor to let you know that, well, this, you know, the stripe indicates that is the negative terminal of the capacitor. You don't want to put it in backwards, because I've done that many times, not understanding this concept when I first started electronics. And what will happen is, before long, you'll burn out the capacitor. If you have current flowing, conventional current flowing, where positive is going up this leg and then down the other leg, you will fry this sucker in a heartbeat. Well, I won't say a heartbeat. It actually takes time, depending on how much current you're pulling, or the voltage that's involved, I should say. What will happen eventually, though, is the top will start to open up, and it will start to let out its electrolytic fluid. Sometimes it happens grandly, and the top will burst open, and it will be a volcano of electrolytic fluid that just goes poof. And other times it happens not so grandly, so it just kind of opens up a little bit and starts to seep out until the capacitor just doesn't work anymore, and things on your circuit start to do weird stuff. That happens sometimes in TVs, because these are also temperature sensitive. is you will have, they will, in like large LED TVs and stuff, there's been problems in the past where these things heat up further than they need to be, and in order to let out some of that steam, the top kind of opens up a bit, lets out electrolytic fluid, and before long you got a capacitor that goes dead in your TV. So the one thing about these capacitors is that they're great and that they're cheap and they're smaller, but they do have a lifespan, and they will die over the course of a 20, 30, 40, 50 year period. Okay, 15. Here we go. What does a capacitor do? Oh crap, went too far. A capacitor holds charge, kind of like a battery, but it will charge a lot faster, but it will release a lot faster as well. And I'm going to show you a demo here later on that. A capacitor has a very low internal resistance, and what that means is that it doesn't have a lot of, like with a battery, if you put a wire across the terminals of a battery, it'll take a little while for that wire to start to heat up. With a capacitor, if you put a wire across the capacitor, it will instantaneously release all of its charge like that. And sometimes that results in a fantastic spark storm. So so just know that what that capacitor is doing is it's there to hold a charge. What are these symbols and what do they represent? So we're getting a little more in the advanced side of things. We're not going to deal with this today, but just so you know, these are both transistors. Transistors come in different forms. You have an NPN and a PNP transistor that are very common, and just kind of to show you in a simplistic way how these work, if you put in an NPN transistor, if there is voltage on the base, you have to eclipse a certain threshold, but if you put voltage on the base, what will happen is it will allow current to flow from this C, which is the collector, to the E, which is the emitter. And so current will flow through. Usually you have this stuck to ground, but a lot of people use this for a switch. So if they want current to flow, what will happen is they'll put voltage here and it'll flow. And Ralph's asking for a demonstration of the spark show. I'll do that in a few minutes, Ralph. But if you put voltage here on the base, it will allow current to flow. A PNP transistor is a little bit different in that if there is no voltage at the base, then current will flow. And so you can arrange these in different ways so that you can get the functionality that you want. If you want it to where, hey, when a certain action happens, I want current to flow to my circuit, then you can set this up to where, all right, well, if there's voltage here, then it'll flow, or you set up to where on a PNP, if there's no voltage here, then current will flow. It just depends on what kind of functionality you want. When you start using transistors for amplifiers, what you're doing is you're kind of dealing with, well, what happens in between? Like when it's when you're taking and you're varying the voltage that's coming into this thing. What if you've got a wave coming in? Like how does it react then? Well, it turns it off and on. Well, how does it turn off? And so like when you start looking at that side of it, then you can start to see how these things can be made into amplifiers. But they're very useful, you've got thousands and upon thousands of these things stuffed into your computer chips these days. I should say thousands, millions of these things. But this is kind of the basic use of it. It's just a really tiny switch, right? An on-off switch. And then finally, and this is it for the questions, is what is this? So this, if you've never seen one before, is a breadboard. This is where you can take and stick components in this thing to make circuits, right? Make things happen, make things glow. And just my camera here a little bit, maybe, yeah. So the way they work is you have some columns here on the side, and you have a field of different things here in the middle. And so on the side, what happens is this conductor right here, or this hole, inside of it is some metal. And that metal runs from this hole all the way down to this hole. in a giant column. So if you hook anything up in this hole, it will be electrically connected to anything down here at this hole. Same thing here on this rail that's marked with blue or negative. If you put anything in this hole right here, it will be electrically connected to a hole down here. They are not, these two columns are not connected to each other. So if you put something on this column, it will not connect to something on this column unless you somehow bridge it. But it's two individual rows. In the field in the center, what happens is everything is in, everything is in columns over here, and this also goes to this side. But in the rows in the center, what happens is this one is electrically connected over here to this, and then this one is connected to this. However, there's a giant gap right here, and this area, this row right here does not jump that chasm, okay? So this row of dots is completely independent from this row of dots over here. They do not connect. And so to kind of show you how this works, here is what it looks like on the inside, right? Here's how the connections look like. We've got these columns connected, these columns connected. In the center, we have rows connected. And to give you a little bit better idea, I have two breadboards here. So this would be the breadboard we're going to be using in class, and I believe if you ordered one off DigiKey, this is what came. But this is what it looks like inside. So you have those columns that are all connected with these metal pieces, right? So from top to bottom. So you can see the one on the left does not connect to the one on the right at all. They are completely independent columns. Then over here in this field, we have these rows. So if we look at row 1, okay, row 1 is completely connected with this metal. You might be thinking like, well, what's that metal actually look like? How does it work? So here is one of the pieces. So this is the metal, and on the side, on the front of it, it's got these little clips. So when I'm putting a component in the hole on the front, what I'm doing is I'm sliding my wire into that clip like that. So now what's going to happen is any say electrons that are, or any charge that's on that wire is now going to energize that whole row. And anything I stick in any one of those other holes is going to be electrically connected to this resistor, right? And that's how the breadboards work. So we will get rid of this. So that's a breadboard. Before we go on, I will show you a demonstration with a capacitor, I believe. So let me grab that. Oh boy, mic's attached to me. All right, let me see. Get down here and get this. Okay, yeah, is this it? Yeah. Can you get me a AA battery, please? Oh, so good question, Richard. Make sure, yeah, I'm still running. Good question. The question is, does this induce any sort of capacitance? Yeah, so a capacitor, like that I'm about to demonstrate, is a capacitor. What's inside of it is just a bunch of plates, right? And so what you do is you charge up one plate. Can you go get me your hammer? You will charge up one side of the plate, and the other side of the plate will have a dearth of electrons. And so as soon as you add, as soon as you hook it up to a battery, you charge up that capacitor. In a breadboard, all it is sometimes is a series of plates. And so what happens is breadboards have a small amount of capacitance in them inherently because of the existence of these close plates. Now, typically this doesn't cause you any sort of problem because if you're using just simple DC circuits, just normal little stuff like we're going to build in here, that is not problematic. Because you're just not dealing, like those small capacitance aren't going to bother you. However, if you're building RF circuits and you're trying to like make an RF transmitter on a breadboard, and you get it all together. Let's say you're making an FM transmitter on a breadboard. You make it all, you dial it in with a adjustable capacitor, everything, and then you were to take that and move it over to an actual prototype or a you solder it into a board. I guarantee you're not going to get the same frequency because the capacitance that is induced onto your circuit because of using a breadboard, because of these close plates, screws up with the frequency that you're messing with. And I know that there's some people that are on the chat that have gone through exercises that in that manner that will attest to that. So let's see. So I've got my so this is a flash camera, right? So these are the disposable cameras, and if you take the paper off of it and you open it up and you start digging in, you'll find you'll find a giant capacitor in here that you can hook some wires to. If you want to make this an actual factual like real taser, you actually stick some nails up here and kind of embed it in here, but this is just more for demonstration. I've got the battery out, and now because it is not meant to be used in this way, I have to remember what way the battery went in this thing. Oh, that's it. All right, so yeah, I just heard the charge. Okay, so hammer. All right, here we go. Oh no! Oh wait, hold on. No! Oh wait, okay, there it goes. The battery snapped in. It scares me every time I do this. There it is. All right. So let me see, is it done? Oh no, it's not done. All right, yep. Okay, we're done now. Okay. So I don't know if you can see this, but it is enough to produce some burn marks on the hammer. It is a fun toy to have around. It is not something though that you want to toy. I'm just watching myself now. Just you touch this thing on YouTube. Yeah, everybody. The comments are rolling in from the delay. But yeah, like it's legit. And if you penetrate skin with this thing, it will it will let you know. And when I built this thing in class, I was in a class with a bunch of Neanderthal-like individuals who found it quite funny all throughout class to go up to their coworkers and test this out throughout the remainder of the class. So everybody was on kind of pins and needles. So we got a bunch of comments rolling in here. Let's see. Yeah, it reminds me of Electro Boom. Yeah. It's he does that stuff a lot. Yeah, but there is a serious capacitor in this thing. So yeah, that's capacitor, right? Another good thing is if you want to play around with it is to take and charge up a capacitor. It looks like this. And if you get one that's the right values and you put enough voltage in it, and you kind of have to do a little trick with some 9-volt batteries to get it in, is to charge this sucker up, and then all you do is you just, if you know, in college it would be looking at your roommate and you're like, hey man, you just throw this at them with no explanation whatsoever, and so their first intuition is to catch it, and when they catch it, it lights them up. Oh, got a question here. Yeah, what size cap in the camera? I don't know. I don't remember. It's been so long since I opened it up. I know that it holds a decently high voltage though, and all cameras of that type hold up because they have to charge that flash up. We've got some photography nerds in the chat that might be able to answer that question. I'm not sure though. I know there is a charging circuit in there, and everybody knows this. Like I should say, everybody my age or older knows this. Like because the old cameras and actually the new cameras, if you have an external flash, not a phone camera, but some of these cameras, the external flash, when you take and you turn that sucker on, you will hear the charge, that kind of kicking in, because there's a circuit in there that's giving it that charge. Yeah, when you hear that noise, you know that there's some serious potential difference going into something in there. Looks like it can cause some damage to an unfortunate person. Yes, this is true. I doubt, Richard, if it's a 1 farad, just because a 1 farad would be a huge capacitor. They do, though, now make some, look this up on YouTube later, look up ultra capacitors or super capacitors. And what that is they found a way to take a 1 farad capacitor that used to be like the size of a beer, like a barrel, and they found a way to pack it down into like the size of a dime. There's some interesting stuff on YouTube with people welding with these small capacitors, and you could very well, I've seen somebody take and stack these things up so that they were cranking their cars with them. So some interesting stuff. So I can modify an old Nikon SB600 flash to do this. Yeah, probably so. That it would, in fact, an old Nikon flash, the right kind with a good flash cube, I would say instead of using it as a taser, it's better to use that as a blinding a blinding thing than it is a taser. Let's see, how can we select value capacitor in CKT? I don't know what CKT is, but can maybe give me some some clarification on that. All right, so let's move along. I've got a, let me reduce the size of my head here. I have this breadboard, and if you look on the website, you were given, or there was a student worksheet. Okay, so we're going to go through this and kind of talk about it real quick. I'm gonna kind of push through this so we can get to the keycad part, because I know some of you guys are kind of versed in electronics, and so we'll kind of quickly pop through this. But demo the taser. Yeah. The thing that you want to what we're going to do is take a look at how we can pick components. Say if we're just going to, oops, sorry about that, hit my mic. How do we pick components? How do we pick LEDs in order to use them in breadboards and try to figure out, what they require and how do they work and all that kind of stuff. So we're going to look at that. Something about an LED that you need to know. A few things really. One, an LED is a polarity sensitive. Okay, so a polarity, the way it works is when you're looking at the LED, it has a long wire and a short wire on it. The longer wire is typically pointed towards the positive terminal of a battery, or the positive input. Okay, so where in this case we're going to be using conventional current flow, or what they call whole flow. And so if you're looking at it in that respect, that longer lead, that longer wire needs to be pointed towards the positive side of the circuit. The shorter wire is towards the negative side, or the ground side of the circuit. Another way you can look at it, because sometimes what happens is these leads start to get the same length, or you bend them all out, is if you look on your LED, if you ordered some of these, if you look on the LED itself, right at the base of it, you're going to see this kind of circular skirt that's on the base of the LED, and one side of the LED of that skirt is flat. That flat side is going to correspond to the shorter lead. And so remember that, because we're going to talk about that when we get into KeyCAD. That flat side there kind of points towards ground. And so that's just kind of two indicators to let you know how you need to hook up an LED. Another thing about an LED is that an LED always requires a certain amount of voltage to turn on, and an LED requires a certain amount of current to keep it from to keep it from blowing up, and two, to have enough current to turn it on. All right. So what you're doing with an LED is you need to give it enough voltage, but B, you got to be able to figure out a way to control the amount of current so it's getting just what it wants. Because if it gets too much, you're going to see a really bright light really fast and then no light at all. And if it gets too little, then you're never going to see anything light up either. So the first question on our sheet says, when looking at light emitting diodes data sheet, there are two critical electrical characteristics that are needed in order to get the component working properly. All right, so A is going to be the forward voltage, and B is going to be the forward current. So that's forward voltage and forward current. So if we take a look at the data sheets that I sent you, so we're going to take a look at this red data sheet. So it says red LED C503. It's one of the things that was in the catalog to order. Let me blow this up a little bit. So what you'll see is you see two different ratings. In every one of these LED data sheets, you're going to have an absolute maximum rating, and in most data sheets, you're going to have an absolute maximum rating. And this is kind of characteristics to let you know how far you can press it to where it's right on the edge, and pretty much you'll get maximum, with an LED, you'll get maximum brightness, but you will, if you run it at that absolute maximum rating, you will compromise the life of the LED. The other set is the typical electrical optical characteristics. And in this part of the data sheet, this is if you put it in this particular range, the LED will operate at its best efficiency, giving you optimal life for the brightness that you have. And so, so what you're looking for is two things. You're looking for current, forward voltage and forward current. And so if we just look at the typical electrical characteristics under forward voltage right over here. Oh, let me get my pen. On forward voltage, they kind of print it up for us. It says that our forward voltage that we can expect typically is 2.1 volts. All right. So it tells us our units in volts, typically right here. And then what it'll do is it'll say under what condition, right, is that. And this is this is the forward current, I sub F. So they want for this LED to operate within parameter to give us a good amount of illumination that'll give us our maximum lifespan. Then we should, we're going to drop 2.1 volts across it. And we need to make it to where there's only 20 milliamps of current running through this LED. So keep that in the back of your mind. We got 2.1 volts and 20 milliamps. So let's go back to the worksheet. And it has something for us to do. So below is the circuit for making an LED glow. Given that it is a red LED, what should be the value of R1 that would allow the LED to operate with optimal performance? When you have determined the value of R1, build this circuit on the breadboard. Remember that the LEDs are polarity sensitive. The longer leg is the positive terminal. So what I'm going to do is I'm going to give you just a few minutes to kind of work this out and try to, figure out like, what you need over here. What it does is it says, what's your voltage source? So in this case, we're using a 9-volt battery. What's the forward voltage? What's the forward current? And then it says, it shows you this V equals IR, and it says, pretty much plug this formula in. You want your voltage source. You want the forward voltage that was coming from the LED chart. You want the forward current that came from the data sheet. And then when you put that in, you're going to be able to solve for this resistor value right here. So I'm going to give you just a few minutes to do that, and I'll be back momentarily, and we will discuss the answer, and we'll plug it into the breadboard and take a look at it. Okay. I see we've already got some people trying to hook it up and got some LEDs that fried, so that's nice. Get that nice aroma wafting through the room of burnt electronics. Unmistakable smell. All right, so we'll go kind of step through this. So our voltage source, let's see. All right, let me put this thing on a pin. So our voltage source in this case is 9 volts. The forward voltage that we said that we needed in order to make the LED work is 2.1. The optimal forward current that we want is 20 milliamps. I'm going to write this a little differently. I'm going to go 0.02 amps. Okay. And it looks like Richard just scored the right answer there, I believe. So V equals IR is what we're looking for. All right, so let me explain this formula a little bit. So all I did was I took V equals IR and I made it to where we could figure out how much, what kind of resistor we're going to need to achieve a certain current if we put the LED in the circuit. All right, so here's what's going to happen. You've got a voltage source and you put an LED in the circuit here. What's going to happen is the data sheet told us that we're going to take that voltage and we're going to drop that voltage by 2.1 volts. Okay, so by the time we've got anything left down here to flop across this resistor, it's going to be 9 volts minus whatever the LED needs to turn on. So in that case, so we end up with 9 volts minus the 2.1 volts, and that's going to be equal to, we're trying to figure out the resistance R1, the current that we want. All right, so the current that we want is 0.02 amps times R1, which is what we're looking for, right? So we can rewrite it to look like this. And if you do all the calculations, you will end up with 345 ohms here. So this is kind of the way that you kind of calculate this. Now, if you have a meter, you could actually hook this up and do the actual IF, and we're probably gonna skip that part. This is kind of a leftover from the class I teach. But hopefully you can see how this kind of gets put together, and we'll test ourselves a little bit further here down below, see if we understand it. But yeah, so you got this voltage source. The LED is going to subtract from that voltage source, and so you're going to be left with an amount of voltage that is what, that's like 6.9 volts left over. So you're going to have 6.9 volts drop across this R1. One thing to remember about voltage in a circuit is that if you start off with a 9 volt source, then pretty much the stuff that chews up the voltage out here has to equal that original source. So if this is going to chew up 2.1, then there's going to be a 6.9 drop across this. All right, they have to add up to this guy right here. And so now if we're looking at this, trying to figure out what R1 should be, well, we know there's going to be 6.9 volts there. We know that what we want is to have 0.02 amps flowing through it. And so if we do the math on that, it says that in order for us to have the correct amount of current flowing through this LED, we need a 345 ohm resistor, right? So you can get kind of sloppy with this, and I'll show you here. So let's look at our breadboard and kind of show you how you hook this stuff up, right? So if I've got a resistor, or let's say I've got an LED, all right, so I've got my red LED here, and I've got a 9 volt battery strap, looks like this, okay? First thing I'm going to do is I'm going to take my 9 volt battery strap and I'm going to hook it into the left side of this board. So I'm going to put my red in the positive, I'm going to put my black in the negative, and so now all the way down this column, I will have positive voltage. All the way down the second column, that's going to be my ground, my return, my negative. Okay. Now, if I want to hook it up according to what we saw here, Okay, I'm going to have a battery that's going to be in line with an LED that's going to be in line with a resistor. Right, so I've got my battery there. The next thing I need is my resistor. So if you look at the schematic, one leg of the resistor touches the battery, the other leg of the resistor touches the resistor. So the way I'm going to do that is I'm going to take one leg, the long leg of my LED, I'm going to put it in the positive column, anywhere on the positive column, it doesn't matter. And I'm going to put the other leg just in the field. I put it on row 4, it doesn't really matter. The next thing I need is my resistor. Okay, so my resistor, it says 345. All right, well 345 is the optimum, and resistors are different, different values. So if you have a 100 ohm resistor, that means that resistor, if it's a 10% resistor, could be as low as 90 or as high as 110, right? And so the closest I've got to that is a 330 ohm. It's close to 345. If I wanted to get really close, so some of the stuff that I asked you to purchase, I believe you have a 100, you have a 150, you have a 330, a 220. So you could make some combinations of those, but the thing is well, I mean, it's pretty close, and electronics sometimes can be a little forgiving. If we look at our maximum, if we went back to that data sheet and looked at our maximum rating, and you redid the math for the resistor of using a 330 instead of a 345, we would still be underneath that maximum. So I'm going to get a resistor that's close, and what I'm going to do is put one leg of it. I'm going to take one leg and put it on the negative leg of the LED, or just in that same row. It doesn't matter where in that same row, but it has to be in that same row. And you'll look on your schematic and see that the other leg of the resistor goes into the negative terminal. So I'm going to drop this into the negative. Okay. So just so hopefully you guys can see that. Just to kind of point out something that is egregious and happens all the time when you're doing this, is if you have a component, I'm just going to use this resistor for instance, and you take this component and you put it, you put both legs. If you look on your breadboard and you see two legs of a component both in the same row, well, know that you have just skipped that component because you just shorted that component out. That metal that's underneath here is connecting this leg to this leg, pretty much making this resistor ineffective. So if you have something coming in, it's actually going to go right over here to the other side. It's never going to go through this resistor. All right. Yeah. So in this case, that is just make sure that if you're using a breadboard, if you see a component and you put both legs in one row, that is not the way this works. What you want is you want it to look like this, right? You want it to go from positive over through to a part of the breadboard, connect that to another component, and then out and then to the negative, right? So you continue that flow. I've seen people take this LED and just stick it, both legs in the same row. Well, that's not going to do anything for you because one, you're not going to get any power from this column, and two, the LED will never come on because you've got a piece of metal that's shorting those two leads together. So the electrons are going to take the path of least resistance, and that is not through the LED. That will be through that metal to the other side. So now what I'm going to do is I'm going to hook this guy up, and we get a nice red glow. So got my 9-volt battery on it. So now we got a nice glow. We've got it going through here, and we can safely turn this guy on. If you hook up the battery and you do not get a glow right away, quickly disconnect the battery. Pull a wire, anything, right? Because you probably got it set up to where you're about to fry something or something's about to burn up. So what I usually like to do when I'm testing is I will put one terminal on, and then I will bring the other one over and just touch it quickly. All right, make sure it works. And if it does work, then I'll go ahead and I'll strap it down. If it doesn't work, then hopefully I haven't left it on there long enough to fry anything. So just a little troubleshooting tip there. So hopefully you guys were able to kind of accomplish that task. It's really hard for me, if it's not working, for me to kind of look over your shoulder and figure out what's going on. But if you go down to, get this here, go down to number 3, it says, using the same circuit above, redo your calculations using the white LED provided. So I'm going to get rid of this red one out of my breadboard, and I'm just going to pull it up. I'm going to leave everything else the same there for just a second. And if you take and look at your data sheet for this, so we're going to go back, get the white one. We'll increase this. You'll scroll down to your typical characteristics here, and you'll notice we got a different voltage drop, right? So we're talking about a 3.2 voltage drop instead of the 2.1. The current's the same, right? So what you're going to do is you're going to go back to your formula up here, and where you have the forward voltage, instead of putting 2.1 there, you're going to put 3.2 there and redo this. And so when you redo this calculation, I believe kind of Richard chimed in there with the answer that you've got a 290 ohm resistor that you're going to need at that point, right? So you've got some decisions to make again, right? So right now we've got a 300 and something. So I'm just going to show you something. So if I wanted a 290 ohm capacitor, I'd take a look at all my values, and I'm like, well, I don't have a 290 ohm there. I got a 120, and I got a 220, and let's see, I've got a 100. So I could stack those two, right? So I could take a 100 and I could take a 220. So I'm going to pull my 330 out. So first, we'll take our white LED, stick it in there. So positive to the field. All right. Then I'm going to take a 220. And I'm going to put that on the negative leg of the LED and have my resistor going down to just another field. So I got this going down to row 10. Then I'm going to take a 100 ohm resistor, and I'm going to put it in series with the current resistor. So I'm going to take, what I'm doing is I'm putting this in the same row, and then I'm taking the other leg and I'm putting it to ground. So in this case, what's going to happen is I can take and I will have my LED, and I can add 220. So that'll give me 320 ohms. That's a little bit higher than 290. Now there are some, and I see David in there mentioned something about parallel. When you mention parallel, you could take some of these resistors and you could put them in parallel to kind of get a more exact value. But the last time what we did is we had a little bit less resistance than we needed. Now we have a little bit more resistance than we needed when we do it in series. And if I put the power to it, let's see, the white LED comes on. Hook it up there. And so you're just kind of playing with the values that you have. And as long as you're close, things will work out. It's kind of the way it kind of works, is get it kind of close. The other thing you can do is if you're just trying to make the thing light up and you really don't care about the luminosity, is you can just go, man. Like you can take and right, like let's say we calculate this thing to be 290, which we did, and all we've got is a 330, right? So all we got is a one that's large. Or let's say even yet, I'm going to go with this 1K resistor. So I got a 1K resistor. So this is 1,000 ohms, right? So it's much more than what we calculated. But if I hook it up, it still glows. It doesn't glow as bright, not near as bright, but it still glows. So the thing is with LEDs is that a lot of times what you can do is you can provide a larger resistor than it needs. Do not go the opposite way though. Do not provide a resistance that is substantially lower, because if you do that, more current's going to flow through it. It'll get really bright, and at some point if you provide too low resistance, it will blow up. So be careful of that. The other thing I want to show you is I'm going to skip on down to number 5 on your sheet, because the thing I want to show you is, let's say you have 3 LEDs that you want to put in series, right? So what that means is I've got an LED there. I'm going to hook another LED to the back of it, like so. And then I'm going to hook another LED to the back of it, like this. So what kind of resistor do we need there? All right, so if we look at our calculation, we look at our data sheet. The data sheet said that it takes 3.2 volts, all right? So 3.2 volts in order to power these things on. Well, our voltage source is 9 volts. So if we go 3.2, I'll go back to the camera here. If we go 3.2 plus 3.2 plus 3.2, that's 9.6 volts. So that's saying that this will chew all of the voltage up. All right, we go back, look at our worksheet here. So if we have this thing chewing up all the voltage, we're going to end up with a negative number on this side. So we're going to have like negative 0.6, and then you take and divide that by the current. Essentially what you end up with is a negative current that doesn't make any sense whatsoever. It kind of does, but it's beyond the explanation of what I want to do today. But essentially what's happening is that this thing is going to chew all the voltage up. So let's just round it. Let's just say 0, all right? So let's say that it's exactly it has exactly 9.6 volts in the battery, that it's going to chew 9.6 volts up. We're just going to round it and say, okay, it's going to be 0. We divide the current number into it, which is 0.02 milliamps. We're going to get 0. It says, well, that means we end up with a resistance of 0. But that makes sense, because the thing is that since these LEDs are chewing up every bit of what we can give it in voltage, then it doesn't need a resistor in order to try to control the current. Now, some people do it anyway. Some people put like a really small resistor on it just because it's not seen as very good practice to do what I'm about to do. But most of the things I do aren't considered good practice. So what I'm going to do now is I just kind of hook this up. So I've got a white LED coming from power. It's going to a second LED. It's then going to a third LED. And finally, it drops into ground or negative. So if I hook this up with my battery, we get all 3 of them lighting up, and we don't need a resistor because we're chewing up pretty much every bit of voltage that it'll provide, and we're actually trying to chew up more. So this isn't exactly, clip my battery down here. This isn't exactly optimal because the LEDs are actually demanding more than the battery can provide. So they're actually a little bit dimmer than they would be if the turn on voltage was somewhere around 3 volts, right? But yeah, so you can stack these so many that before long you don't even need a resistor. It is important though to stack these in the same value. So if I take one of these red LEDs and stick it in there, this is going to be crazy because this might blow something up, but that's okay. Let's see what happens. This doesn't work out as well. Right, it did there just because it happens to have enough voltage, but you can't see it because of the way that it's set up. But there's one that is a lot more illuminated than the other 2. The red one was a lot more illuminated than the other 2 because it had more voltage than it needs, and this probably should need a resistor on there. But when you start mixing and matching LEDs that have different power requirements, you have to be a little bit careful about that because you can inadvertently burn one out early. Like that red LED would probably burn out faster than the 2 white ones because there's more than it needs there. All right, cool. So we got a few things here. Let's see. Can you please make a video on how to use isolation transformer with oscope to do a measurement? Maybe one day. Capacitors in parallel equal resistors in series in relation to knowing when to add values for capacitors. Yeah, so we've been talking about like taking resistors and putting them in series to add. With a capacitor, it's different. With a capacitor, in order to add them together, you need to put them in parallel. It's exactly the opposite, and it's infuriating and frustrating when you're trying to learn that in school. Yeah, if you put a capacitor in series, you will decrease the overall capacitance. If you put them in parallel, you will increase the overall capacitance. There's one more thing I want to show you. So you can go on it through and play around with the rest of this, the sheet. Actually, I do want to show you number 6 in the sheet because it does bear some weight on what we're about to do in KiCad. Yeah, we can still do it in KiCad. It says, all right, so let's say you've got 2 white LEDs and they're in parallel, right? So that means I've got this guy coming out of, I've got 1 coming out of red, I've got 2 coming out of red. So I'm going to do it here. A lot of people forget that you can use all of your breadboard, right? So I've got an LED coming out of the positive, I got an LED coming out of the positive, just like I do here in my schematic. So right here I got an LED coming out of positive, I got an LED coming out of positive. All right, then it says we got a resistor coming out and we got a resistor coming out of both of these. And it says place 2 white LEDs in parallel as seen below. What are the values of R1 and R2? Okay. So yeah, so sorry, just reading the comments here. So what you want to do is, in this case, let's figure this out. So we got 9 volts, and it's 9 volts across this leg, and it's 9 volt across this leg. And if you look at this and you start to do the math, what you realize is that this problem and figuring out what the resistor should be is the exact same as this problem. Or I should say, in this case, we're using the white, so it's number 3. So what you're doing is you will calculate the resistor for a single leg for a white LED. And we've already determined what that is. We determined that it's going to be 290 ohms. And so what you're going to do is you're going to put the same resistor value here that you would on the one with the single leg. And so David just said, put it in, comment said the same. Yeah, it is the same. And so if you take and you put in, say, a 290 ohmer here and here. So I'm just going to take a 330 because it's close to it. This will work all right. I get out my 2 330s here. I'm going to take and put a 330 at the end of this guy. And then here. Oh, by the way, I'm working on this thing while it's energized, so let you know more stuff that I probably shouldn't be doing. And this guy here. So what I have is one of them powered, and let me bend this out of the way so you can see it. So this guy comes from positive into here. The resistor picks it up, goes to negative. Same here. Positive, picks it up, goes here, goes to negative. So when I hook this guy in, it glows. Now the thing is, well, is this the same circuit as a single leg? Well, no, it's not. Then how can we get away with using the same resistor? Well, we do pay a price. So we do have 9 volts, and we're dropping to 3.1 volts in here. We're dropping 3.1 volts in here. Each one of these guys is going to be pulling on each individual leg 20 milliamps. All right, so we got 20 milliamps here, 20 milliamps here. The difference is the battery, though, is now supplying 40 milliamps. All right, so in the single leg setup, we were only supplying 20 milliamps for that single leg. But now since there's 2 legs, we just set this thing up to where we'll pull 20 milliamps here and 20 milliamps here. That means the battery has to supply twice as much. So every parallel circuit you put on this, so if you keep stacking LEDs, you're asking the battery to provide more and more current, and your battery will drop faster. So right now when I hook this up, it is supplying twice as much current to run this circuit than it would to run a normal circuit. The one thing about this is that you can't just get current out of thin air, right? And so if you're pulling 0.02 here and you set this up to pull 0.02 here, we'll know that now your battery is giving you twice as much because it has to in order to supply enough for each individual leg. So hopefully that makes sense. See, would this be a good way to mix and match LEDs if need be? Ben, yeah, so Ben, I've done this, and I've had students who've done this in the past. There's some LED projects that we do in the class, a lot of heavy LED projects, and they want to start mixing and matching LEDs. And so, yeah, so what you do is you start building those branches out and making sure that you provide the right resistor for each branch so that you are controlling the current for every one of those LEDs. So that is one way to do it. I have been told though that it's not the smartest way to do it. It's better to have like an LED driver and some different things. But for my applications, it's never been a huge issue. I will show you this kind of an interesting thing. So I have here that massive capacitor that I was messing with earlier. And so what I'm going to do is I'm just going to take and I'm going to stick this across the positive and negative. So I'll bend this down. So I've got the negative end in negative, and I got positive and positive. So there's my stripe on the back going into the negative there. And I've got it hooked to a battery. And so I just got this cap there. Now what's happening is these are powered up, and as soon as I put that cap in, it took a charge from the battery. So this guy right now is completely charged up from the battery. I'm going to disconnect the battery and show you what happens. So you notice that the LED doesn't completely go out like right away. And if we really wanted to see that even in more action there, I can take out one of them. I'm going to energize this guy back on, disconnect it, and you'll see that single LED will stay on a lot longer than just the two. Okay? So we got that. And it's still glowing. Yeah. So it'll stay lit very dimly for a nice long time. So these capacitors can, like I said, they supply. You can charge them up fast, but they also kind of release everything fairly fast. If I change that out for the red one that has a lower voltage, it will hang on even longer. Yeah, actually, I'm plugging this in and it's glowing in my hand because there's still enough voltage in the capacitor to keep it going, and it'll stay lit for a long time. The thing is, I can take the capacitor out, and I can come back, put the capacitor back in, and there's still enough voltage for it to continue on. And somebody said earlier, you got to watch out for a capacitor because sometimes it's never truly discharged. Yeah, that's true. Sometimes it's not discharged. You've got to take and discharge it on something. So I'm going to take a wire from a resistor and just discharge it there. Cool. So fun little trick. So let's get into KiCad. All right, so we've got, what we're going to do is we're going to take this circuit here that's in our, that's in this final form, this 2 LEDs and 2 resistors. And let's say we wanted to make this into a PCB. So we want to take and take this kind of this circuit, and we want to build it out and make it and have it shipped off. So let's see, I'm working on third. Yeah, okay. So let's take a look at what that would look like. So what you're going to want to do is take and run KiCad or KiCad, whatever you want to call it. So let's see, there it is. Takes a little while to. And I tested out this circuit earlier just to make sure I wasn't an idiot and didn't mess something up. But what you want to do is make a new project. So once you open up KiCad, it'll give you this, which is kind of your base of operations. It keeps track of all your files. So if you click on New and then go to Project, click the folder where you want to have your project folder. So for instance, wherever you decide to place your this project file, it's going to create a folder for you in that place and then put all the files beneath it. So don't create a folder manually and then put it in that, or you'll be 2 folders deep at that point. So I'm just going to call this test number 2. And this is going to create a folder for me in this and then put all my files in that folder. So test 2. And we have 2 files that it creates for us. What we want to do is start with our schematic. So there's this first button is called the Schematic Layout Editor. Click it. And I've got a bunch of conflicts because I've been doing all kinds of crazy stuff. Don't worry about that. So this is the page that is brought up. You can use your mouse wheel to zoom in and out if you're on a laptop. Oh, I'm sorry, man. But it's rather difficult to navigate without the mouse wheel. I think there might be a way to manually zoom in and out. Maybe if somebody finds a way to do it on your laptop, throw it in the comments. Yeah, the mouse wheel seems to work fine to zoom in and out. What you want to do is the first thing, let me get my plans out here so we can go through it, is the first thing we want to do is place our components, right? Over here on the right hand side is a little place symbol button. You want to click that and it's going to bring up a little pencil with a crosshair, and you're going to pick where you want to place that component. I'm going to click in the middle, and the first time you do it, it's going to load all the libraries that you have available to you. It brings up this little nice library here, and the first thing I want to do is I want to put in a battery. So I'm going to type in battery, and it will display for me all the different battery selections. I'm going to want this single cell battery, so I'm going to highlight single cell and then click OK. And you can see that just down there a little bit you got a symbol, so I'm going to zoom in so I can take a look at that symbol. And you can drag this around and place it wherever you want it. Just click it and you're good. Now, after you put the battery cell down, if you click again, it'll bring this dialog window back up. And the next thing I'm going to want is an LED. So I type in LED. It shows me an LED there. And so I'm going to select it and place it. Now, one of the things you can do is if you need, we're going to place 2 LEDs. Now I can go back into that same dialog box if I want to, but there's some hotkeys that come in really handy that I'm going to teach you. The first is C. If you press C, then it will make a copy of the thing you just put down, or the thing that you held your, so go over that again. Hold your cursor over the component you want to copy, press C, and it'll make that copy. And then you can lay it down. The next thing we're going to want is a resistor. So I'm going to go in here and type resistor. And there are different, and actually you can just put R as well. So if you just put R, it'll pop up, or you can type out fully resistor. There is a resistor I like to use. If you scroll down, you'll see like the normal R for resistor, but then you see one RUS. So if you're a true American, you will choose the RS resistor R from the US. No, but the reason I like this one is because I like the squiggly line that the resistor makes on the schematic. I'd rather have that than the box that's there. You can pick out the freedom resistor there and click it, and then hit C to make a copy of it, and there you go. The other component, or the other hotkey that you want to kind of memorize is M. So I've already placed everything. What I'm going to do is go back up here and click my arrow button instead of the place value, the place symbol button, because it helps you to do things a lot easier. But now I can hit M and start moving these things around. So hold your cursor over the thing that you want to move. You hit M and then you just move it around. The other one, so we got C, we got M. The last one is R for rotate. So I've got some LEDs here that I'd like to rotate in a particular direction. So I am going to press R and rotate these down. The way I remember how this kind of works, if you look back at our schematic, you can look at our schematic if you want to, and that's a great way to do it. But in our schematic, you'll notice that how the LEDs are oriented. The triangle of the LED is pointed down towards ground. I always kind of look at it as you have some currents flowing from positive to negative, the whole flow current going through, and so your triangle's kind of pointing in the direction of the current flow. So you just kind of make sure that you arrange that correctly on your schematic. So I've got my two LEDs, arranged in that manner, and then my resistor. Really the last thing I'm going to do as far as component placement now is I'm going to now put some wires in. So if you go all the way over to the right hand side of the screen, there's a button called Place Wire. So you click that, and you're going to go over to your battery, click on the top of the terminal, and you'll see a little green line emerge out of it. So you can do this a number of ways. Every time you kind of make an angle or kind of roll around here, you'll see it's trying to match you and try to figure out which way you want to go. So I usually kind of, if you go straight over, sometimes it likes to bend down and then come up, which is very hard to deal with. So you can come up, and if you want it to kind of go to here and you want to make sure it doesn't bend oddly, you can actually click at this corner, and then it'll stabilize at that corner so it doesn't do anything strange for you. So I'll click there, I'm going to click just above it, and I'm going to drop it down to there. So we've got one line built. I also need to power this LED over here. So what I'll do is I can click from this LED, come over here, and click there, and bring it over here, and click on this junction, and it'll make a little green point to let you know that you've just connected 3 wires together. So you've got a junction there, and that's every time you connect wires like this, it'll give you that junction. At this point, now we're just connecting up the rest of the points. So we click here, bring the wire down to here, click here, bring the wire down to here, and you can do the rest however you want to. Just going to bring it over to here, and then I'll go from here to create the junction. So there we go. We've kind of built our setup here. Now, so we've got our schematic built. Now what we want to do is we want to make sure that we help ourselves, our future selves, that we don't mess ourselves over. So if you come up here, click on the normal arrow key. And what we're going to do is change some of the references. Well, actually, let me roll this back a little bit. Once you got it built, the first thing to do, I would say, is you want to annotate all of your components. So right now you see where it says D question mark, D question mark, R question mark, R question mark, BT question mark. So these are the labels for those components. And you could sit here and call this D1, this D2, this R1, this R2, do it all manually. But KiCad has a way of doing it automatically for you. So if you go to the top, there's a button right by the little bug button that says Annotate Schematic Symbols. Click it. You'll see a little dialog box that'll pop up that has a bunch of things, but pretty much the default value is fine, everything they have here. And if you click the Annotate button, I'm going to move this out of the way so that you can see D1, D2, you can see these. They all have question marks on them. As soon as I click Annotate, it calls this D1, this D2, this R1, this R2, and even over here, BT1. So it automatically takes and assigns a value for each one of these guys. Next thing I want to do is kind of make it to where I understand which each one of these components are. So if I right click on the component and I go to Properties, the thing we just changed was the reference, but I want to edit the value. So if I click that, it says, okay, what I'm doing is I'm editing where it says LED. Let's say months down the road I get this thing and I'm like, well, what LEDs were I using? So what I'm going to say is I'm going to say that was the white LED. So I'm going to put WH LED. And there's also a way to do, there's a hotkey for this, it's V. So if you right click on it and you see just edit value, you can right click on the component and go to Properties and edit value, or you can right click on the value and click edit value, or you can just hit V and it brings it up. I'm going to take white LED. Down here for the resistors, what I want to do is I want to change this so that it is a, I know the value of the resistor. So in this case, it's going to be the 290 is what we said, so 290 ohms. And I'm going to change this as well to 290 ohms. Little trick that I picked up, if you are editing the value and you actually want to put ohms in, like like this, so that's the ohm value symbol. Is the way what you type is you hold down the Alt button on your keyboard, and then on your number pad type in 234. So Alt 234. It's an Alt code, and it will pop up the ohm symbol for you. So get V over here, hit Alt 234, and it gives me the ohm symbol. So yeah, the last thing I'll do is edit my value for my battery. And this, of course, is 9 volts. All right, sweet. So we've kind of called everything what we wanted to call it. We've notated everything. The last thing we want to do is we want to check it to make sure everything's connected. Because sometimes what happens is you'll draw a wire and for whatever reason you won't place it right on the right point, or things just get mixed up. This little bug is called the electrical rule checker. So if you click it, it gives you this sort of thing, and you can run it. And when it runs, it says finished up here in the message. That it didn't give us any errors, so that's cool. If it does give you an error, you need to figure out what that is. You click on the error in the error list, it'll point to it. A lot of times common things are that you didn't connect it upright, like you went through a component and connected it on the side and ended up connecting stuff, and your wires are screwed up and you need to delete your wires and try again. Other thing happens, there's this really weird error when you're using different active and passive components that we're not using, especially when you're using IC chips where it wants certain voltage, it wants certain types of pins on certain types of stuff. It's kind of a pain. Really beyond the scope of what we're going to look at today, but yeah, this is a good thing to see if you've got kind of any errors or anything unconnected. Over from that button, so we're just going down the list of buttons here. The next thing we have to do is we've defined all of these different components, all these different symbols that we have in our schematic. Now what we need to do is we need to assign a footprint. So we need to assign what the actual component is going to be for each one of these symbols that we put up here. The way we do that is we come up here to assign PCB footprints to schematic symbols and click it. And it's going to open up a whole new window. It's going to go out, it's going to fetch some libraries, bring it back. And what it's going to ask us to do is it's going to list every one of our symbols, and it's going to ask us to assign a footprint to that particular symbol. So for instance, resistor. So I'm going to start with R1 here, just to kind of display this. So if you click on R1, you'll see there's a bunch of libraries over here to the left. What we're going to do is come down, and I want the resistor that I use to be a through-hole resistor. So I'm going to click on where it says resistors through-hole on this library, and it's going to give me an absolute ton of different resistors over here to use. But the thing that it kind of gives you in the description over here is measurements, right? So it says, all right, so this number 22 is a resistor, a through-hole resistor with a length of 9 millimeters, a depth of 3.2 millimeters. I believe that's a pitch of 2.54. We'll talk about that in a second. And it is a vertically positioned resistor, which means that it sits on the board sticking straight up. I would rather have a resistor that's laying down on the board horizontal, so I'm going to be paying more attention to the ones that say horizontal over here. Somebody's saying the libraries are taking a little while to load. Yeah, they can do that. So we're in resistors and through hole, and we're looking at R1. So the way that we figure out what resistor we want to use is look at what resistors we ordered, right? Or what resistors we want to order. So what you want to do is go back to one of the sheets that I sent you. I sent you this, let me open up this. So I'm going to open up the list of stuff that I asked you to get eventually, maybe. Looks like there might be a lot of people on it right now. There it goes. Sweet. Okay. Yeah, there's several people looking there. All right, yeah, so everybody's looking at it. So I'm going to open up my list of components, and I'm going to open up this data sheet, this Yageo LR CFR. Right. So what this is a data sheet that kind of gives us some insight into some of the resistors that we ordered. So I'm going to take and look at, let's see, what resistor. I'm going to look at the, so what I have right here is the Yageo resistor, but the resistors, so we want to use the 330 resistor for this, and that's a different data sheet. But I looked it up earlier, and the data sheet for the 220 and the 150. No, wait, no, actually, we are the right data sheet. In just a second, make sure, double checking here. So this is the Yageo. All right, yeah. So what we're going to do is we're going to use the data sheet for the 220 ohm resistor, even though the measurements are the same for the 330 ohm. It's a different company, but I just kind of want to show you how this works. All right. So what this says is that this resistor has a manufacturer part number of CFR-25JB. And if I look down here, it shows me these dimensions for the resistor on the data sheet. And it says anything that says CFR 25, and let me go back here and look. All right, CFR 25, that the dimensions are going to be 6.3 millimeters in length, 2.4 millimeters in diameter, and the height of this thing is, get a little closer here, so that's the height of the leads, the wires, is 28 millimeters. So we're looking at this length, 6.3 and 2.4. So if I go back to my schematic, oh, no, sorry, wrong part. If I go back to the footprint assignment, I will look over here at the resistors, and I will see we've got a few resistors. We got two horizontals here, and I'm just want to make sure that I get the one I'm looking for. Yeah, so we've got two horizontal resistors here. We got a 6.3 millimeter, which is the length we want, and the diameter is 2.5, so that's great. And it says that our horizontal pitch, so what the pitch is the pitch is the distance between the two soldering points where you're going to slide the wires into. So I've got a 6.3 millimeter resistor, and in this one I got a 7.62 millimeter 7.62 millimeter distance between the two holes it's supposed to slide into. Now I know from experience, and usually what would happen is I would pick that one. I would pick this particular one, number 19. Because what will happen is you'll take that resistor and you'll have to bend those wires really, really close to the resistor, and it will be a very tight fit to be able to get that resistor in that pitch, that 7.62 millimeter. So that's a little bit too tight, I think, for when you're dealing with this stuff, just kind of beginning. So I'm going to go with the footprint just below it. So 6.3 millimeters, 2.5 millimeter diameter, and a 10.16 millimeter pitch. So that gives you a few millimeters on either side of the resistor to be able to drop those wires into. The great thing about KiCad too is that if you want to see what that looks like, you can come up here and click this little magnifying glass, and it will show you a picture of what that layout's going to look like. So here we have our 6.2 millimeter resistor kind of area here, and then I've got two copper holes 10 millimeters apart where I'm going to drop the wires in. Now, how do I know this is 10 millimeters apart? Well, I did it last night, but the other thing is, if you click over here on the left-hand side, there's a measuring tool. It says measure distance between 2 points. I can click it. I can click over here on this. I can drag it over to here, and it'll say right there 10 millimeters. So nice little measuring tool they put in here to be able to help you out. The other thing that's interesting is they have a 3D view up here at the top. So 3D display, click it, and not all components will work. but you can zoom in and then grab it with your mouse and kind of look to see like, oh, so this is what it's going to look like whenever I solder this thing in. So I can see that I've got a 6.3 millimeter resistor here, and there's going to be a little bit of wire extra on the end before it goes in the hole. If I look at the other one, the 7.62 millimeter pitch, look at that 3D display, you'll notice that, okay, like that is a really sharp bend right next to the resistor, and there's not a lot of room for play, so you got to be serious about what you're doing. So we're going to pick the 10.16 millimeter pitch. If you double click on it, it will then, oops, sorry, touching the mic here. If you double click on it, it will then populate that blank, and then I'm going to do the same thing for R2, pick the same exact one. Okay, so we populated both of those. The next thing we want to do is pick the LEDs, and this is really simple. You go over here to the library, you click LEDs, it gives you a bunch of LEDs. Now these LEDs, if you were to look at the data sheet, they have a diameter of 5 millimeters, and there is right here on the side LED diameter 5 millimeters. It is the common one that's always used. They've got all kind of different special LEDs you can put in. They got surface mount, all kind of stuff. Hand soldered surface mount, like specific brands, but this works fine. Just a 5 millimeter LED. I'm going to click it for that one. I'm going to double click it for that one. The last thing we need is a battery. So typically what you do is you have a battery holder that you would use, we don't need a huge battery holder on this thing. I'm just going to take and make a solder point for this 9-volt battery strap. So I just need, pretty much all I need is 2 holes. And that's kind of, I kind of had to search through and find this. This was something I had, this is why I did it ahead of time so I could make sure I get the right one. But if you go to the library called Connect, under Connect, there is it's called Pinhead. Let's see, where's that? Yep, Pinhead 1-2. We can take a look at it. All it is 2 solder points. That's it. So I'm going to click that, and that will populate the battery component for me. So we're good here. We've got everything populated. The next thing that we want to do is down here where it says Apply, Save Schematic, and Continue. Click it. And it'll save everything up, and then click OK. And it will bounce us right back to our schematic. All right? So now we've assigned those values, and what we want to do is before we move on to start placing those on an actual PCB is we want to do something called generating a net list. And what it is a list for the PCB software that says this symbol equals this schematic part. I know we just did that earlier, but what it's going to do is take that list we just made and it's going to generate a specialized list for the PCB software. So if we click where it says Generate Net List, all we got to do is click Generate Net List. And then it'll come up and ask you to save it as a .NET file. That's fine. Just keep everything default and just hit Save, and you're good to go. Okay. And so kind of the next step is now we want to take all of those symbols we picked and lay them on a PCB board. To do that, you're going to click this little button up here. It says Run PCB New. And it's going to bring up kind of a black background screen with some layers over here on the side. So what we're going to need to do is first thing is come up here and load that net list. We're going to load that list that we've been building the whole time. So you click Load Net List, and then click the little button over here for Open, so the little folder, and you're going to see your net list file that you just made. Click Open and click Update PCB. Then you can hit Close. And some of you, you're going to see a blank screen. Don't click anything. Just take and roll your mouse button out, and you will notice there's a batch of components that are just kind of flying out here in the space. Take that batch and just put it in the middle of this red box and click. If you clicked away and now your components are floating out here in space, all you got to do is highlight them all, hit the M button for move, and then you can move them to where you need to. But once you've got them in place, zoom in close as you can. So now what we want to do is we want to arrange these things so it makes sense to us when we're building it. And what you're going to notice is I'm going to take and hit M on a component. And I should warn you, if you press M on one of these words that is associated with a component or one of these symbols, it will just want to move that, all right? You can hit escape and get out of that. So you really want to press M on the component. If it's one of these other things, it'll move that instead. So yeah, if you accidentally hit it on the text, just hit escape and you're fine. The other thing you'll notice if I'm moving the component is you have these little wires, these white fly wires that are moving around. So what that's doing is that's telling you that this component that you're moving has to connect to this other component. And it's giving you kind of a ghost wire to let you know that these two things are going to have to be connected at some point. So what I'm going to do is I'm going to put my 9-volt piece kind of down here. I'm going to take my two LED, see there, I grabbed text instead. Zoom in, grab my component. I'm going to move an LED, D1, kind of up here. I'm going to move D2 up here. I'm going to move a resistor for R1 here, and my resistor R2 here. Next thing I'm going to do is I'm going to rotate R1 and R2, and I'm going to rotate them all. This top one, it says D1. I'm going to rotate it so that this flat edge, remember what we said earlier about the LED, when you have that flat skirt edge, that's considered the negative side. Yeah, so it says, question here. My components are grouped. Is there an ungroup? Yeah, so what you can do is you can click off to the side and it usually ungroups it. If you right click, there is, I think there is there used to be kind of an ungroup thing. Yeah, if they're all grouped together like that and you hit M, it will move all of them. But if you just click off of the field somewhere, it should unhighlight them, and then you can highlight them individually, or you can press things on them individually and move them. Cool. Yeah, good. So there you click off the group. Yeah. So I'm going to take and I'm going to rotate these. So like we said, that flat edge on the LED is the negative one. The interesting thing about this is about LEDs when you're talking about PCBs is that the LEDs, all of the other components, pin 1 is seen as kind of like the I guess you say the positive pin, but pin 1 is kind of where the kind of connection comes into it. And so like the resistors, pin 1, right? Like you've got it coming from here to pin 1 going out of pin 2 back to ground. LEDs are the opposite. So kind of pin 2 is seen as the positive terminal, for lack of a better word, and pin 1 is seen as the negative. And so when you're looking at this, you see this little flat edge on the symbol diagram to let you know, like, oh yeah, this is the negative side. So just kind of put that in the back of your mind. It's kind of an eccentricity of this field and laying out PCBs. So I'm going to rotate those two diodes so that kind of the positive terminals are up. I'm going to rotate these two around so that I know I'm going to place a straight wire between kind of, the number 1 pin here and the ground pin of the LED. I'm going to rotate this around too, hit R, and kind of set it up this way. Cool. And see if I can snap this in a little better. There we go. All right. The next thing we want to do is we want to be able to draw some wires. So I'm going to come over here to the wire drawing mechanism. So there's a little, it says route tracks. So we're going to do that. We're going to route some tracks here. So I'm going to go from, and it tells me what I need to connect, right? So first thing it says is I need to connect, I'm going to connect this guy to this guy. I'm going to connect this guy to this guy. And you'll notice that these are red, because what happens by default when you click the route track is that it puts all of the copper tracks on the top layer, the front layer. So it shows right here this little arrow next to where it says FCU. This means front copper layer. All right. So we're drawing these in. I'm going to draw this to here. Draw this to here. So, yeah, there we go. All right, so there is one more line I haven't put in place yet, and I've done that intentionally because I wanted to show you an interesting piece of this. I could draw this line up, over, around, and to there, all right, and make it work that way. The other thing I can do, though, is I could take, and let's say there are wires in the way, is I don't need to kind of do this weird routing around everything. What I can do is, make sure I didn't make a mark, yep, is I can put the wire on a different layer. So if I click my, my route tracks button and then I click on back copper, I can run a wire from here straight up to here. And it's going to cross over this, but it's not really crossing over it. What it's doing is it's crossing under it. Right now I've got the back copper layer highlighted, so it brings it to the foreground. If I click on front copper layer, it drops that to the back. And so that lets me know this green wire is on the back side of the PCB. The red wires are on the front side of the PCB. All right, let me see where I am on my plan here. Another piece you can do is you can add what I call silk screens to your PCB. So if I come down here to text and then click text, and I click anywhere I want to, I can say this is a product of Skinny R&D, okay? My layer that I do this, I want to put this on what's called the front silk screen layer. So this is the layer where you can, the PCB where you can write stuff on the PCB. It's the same layer that where it says R1 and D1 and D2 on your symbols here. Like these are all going to be printed on the silk screen layer. So I'm going to say front silk screen, hit OK, and then it lets me place this wherever I want. If I wanted something on the back side, I could click and go, let's say, just put test and go to back silk screen. You'll notice, so it's there. So this is going to be printed on the back, but that's problematic. The reason it's problematic is because this needs to be in reverse, right? So if I'm looking at it on the back silk screen, type test, I can click mirrored. Now it's right. Because the thing is if it's on the back silk screen, but I'm reading it perfectly, looking at me, that means that when it comes to me from the manufacturer, it's going to be in reverse on the back. So what has to happen is, this is as if I printed it on the back of the board, and then if you take this schematic, or you take this layout and you flip it in your mind, then test will be written the correct way. So anything you put on the back needs to be mirrored. Anything you need to be on the front is regular. So, so when you're doing this, make sure that you always, if you write something on the back, that you mirror it so that it comes out looking right. The other thing that you want to do is you want to add stuff on the silk screen to make pieces helpful, right? So if you get this back from the manufacturer and like, well, these LEDs up here, these are going to have to be polarity sensitive, and I've got to remember what orientation to put these LEDs in. Let's say that little, like, you know, that little cut there in the skirt, like you don't remember that. So what I can do, and I do this for my students in class for boards that I have them put together, is I will take and add a positive, oh, that was the wrong thing. I will add a positive mark or a plus sign to the silk screen and put it right here by the diode, right here by the LED, so I can remember which one of these pins is supposed to be positive. And really just kind of to let your student know, or if somebody else is building this thing, which side is positive so they can take a look. Now, the last thing that you want to do to kind of, I guess, finish up the board part of this is you have to put in board edges. So you have to let the manufacturer know, all right, where are the edges of this board? So what you're going to do is on the layers, you come down here to where it says edge cuts and click edge cuts. Then you're going to take and go to where you have this add graphic line. You're going to click that, and what you're going to do is you're going to draw the edge cuts with this graphic line. So I'm going to start it here. I'm going to click and then drag that line down to here. And then it doesn't have to be square, so I can go to here, 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 and then I'm going to zoom in, because when you do this, what's going to happen is when you line up the two ends, you'll get this little target mark, this little circle. When you see the circle, that's when you click, and that's when it will assuredly be connected. If you don't see that circle, don't press it. So there, all right. So now we're all connected up. We've got our board edges. Kind of got it put together here. Something else you should be aware of is that anything, all this writing that you see in gray, where it says like 290 ohms, 290 ohms, white LED, white LED, that will not be printed on the board. That is a comment. And so I believe that is the, front fab. So those are comments that you're sending to the manufacturer. So back and front fab. But those are not things that are actually going to show up in the print. The only thing that's going to show up in the print is the stuff that's on the silk screen. So there's that. Let's see. Another thing, let's look into my notes here. Yeah, all right. So I think we're just about done. Cool. So you've built your PCB. The one thing that you want to make sure that you do is pay attention to two things. And just kind of go back up here to your general purpose mouse tool, click off. Look at the bottom left. There's a series of things. It says pads, vias, all this stuff. It says unrouted. If that has a 1 or a 2 or something like that, it means that you have not connected up a wire, and you do not want to send this off to fab with anything right there. Believe me, because it will come back not complete. The other thing that you want to do is up here, there's a DRC check or design rule check. KiCad has some rules that are in it that kind of says, well, these are kind of some commonplace rules that manufacturers use. For instance, like two wires being too close together, or wires being too close to the edge, or things like that, or things not being connected. You can run this, and it will go through and check the tracks, the zones, all kind of different things. Also, you can click list unconnected, and it'll show you anything that's not been connected. But this is a good thing to run anytime you are about to have it manufactured. So I've run that. I'm going to save it. Come up here, just hit save board, and we've got us a usable board now. So there's one less thing that you got to do if you're going to send this off to manufacturing, and that's you have to create something called Gerber files. And what Gerber files are files of each one of these layers, so that the PCB manufacturer knows what to do at each layer of the circuit board. If I go, if I go to File and go to Plot, what you're going to see is you're going to see some stuff that pops up. Now, because of the type of circuit board we're using, some circuit boards, if you send this off to a manufacturer and you're going to have the manufacturer put all the components on it for you, like surface mount components, you're going to need the layers like the F and B adhes. So this is like if you want the components like glued down, so that when they flip the board upside down in the oven, the components don't fall off when they're trying to solder the things down, then you would send these layers off. However, our board is just a through-hole board we're just going to solder stuff into, so I do not send those off to the manufacturer, all right? Likewise, you probably get away with not sending the paste either. It's just a habit. I've always had that there because that's if you're sending off to a manufacturer also to have components put on, then they will. You're telling them this is the one you want to put paste on. I don't know why. I just always have them on, but it's just a habit, I guess. But all these other ones you don't have to send off, right? So I usually have just about, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 layers that I keep on. And the other stuff, plot format should be Gerber. There's some other things in here I found that should be turned on. Hit the mic again. Should be turned on or off. I like these settings. But once you've got everything set up like you want it, you hit plot, and it will create a bunch of files for you with the extension GBR. The last thing you want to do as far as this is you have to tell the manufacturer where you want it to drill the holes through the board, and that's through a drill file. So if you click at the bottom right where it says generate drill files, you're going to have this sort of a screen that pops up. I use the PTH, NPTH in a single file option. Use route command. I'm set up in this way. You can see I use PostScript for the file map. Then just click generate drill file. You don't even have to specify anything up here. It will just take and call, like it did here, just take your project name and put DRL on the end of the file, which is fine. So you just generate it and you're good. Close both of these. And I will show you 2 ways that you can get your stuff manufactured. The easy button way, as far as being able to just uploading simplicity, is to use a place called OSH Park. It's in the United States. Their production time is average. They do good quality stuff. And the great thing is you don't have to give it a Gerber file to get started if you don't want to, because they will take KiCad files natively. So if I click Browse for Files and I go over here to my folder, what I can do is I can just give them the KiCad PCB file. So that is the file that has the schematic layout, or not schematic layout. That's the file that has all of the component layout that we just finished up. So I can click that, hit open, and then it will upload my design. I usually use OSH Park anyway, just to upload the design, to take a look at all the layers to make sure I didn't screw something up. And then I might use another manufacturer depending on what my time horizon is for getting the stuff back. But see, they show you a nice layout of what the board's supposed to look like. They show you, okay, well, this is what it's going to look like. This is generally the square inches, like what it looks like. Hit continue. Well, let me just type something in here. Yeah, you can log in. But if you hit continue, what happens is it will even show you more layers and more stuff and kind of give you an idea of how this thing's going to come out. The other thing that I just found out, which I love, is JLC PCB. This is in China. However, it is super fast and ridiculously cheap. Like the other one, I think that board, I've got it. Just put it this way: it's a lot cheaper to go with JLC PCB, and it's faster. If you have a hang up with it coming from China, well, that's on you. And I'd use OSH Park or something else, because I think OSH Park is all in the United States. I think even the manufacturing is. But God, this is so fast and it's so nice. The way you do it here is you go and you click on. In our case, we'll have a 2-layer board. So you click Quote Now. And then what you do is go to your file where you saved all this stuff. So I'm going to go to mine. Classes, live streams. All right. And here's my file. All right. So here's all these Gerber files that we made. So what I'm going to do is I'm going to take and I'm going to hold down my control key and I'm going to select every file that has a GBR extension. And then I'm also going to select the drill file as well. So I've got every file here with GBR and the drill file. Then I'm going to right click and I'm going to send it to a compressed zip folder. Name it test2. Okay, good. So now I've got all of these Gerber files and the drill file in the test. Come back over to PCB, the JLC PCB, add the Gerber file, but instead of sending it Gerber files, what I'm going to send it is that zip file. It's going to process it, and then it's going to pop up an example here so we can take a look at it. You can also get more detail by going to the Gerber view and messing around with it. And then it's going to ask you what you want. So this is a two-layer board. It's just front and back. You can see you got a trace on the back stuff. It's always, one layer board. I've never really, if you use through-hole components, it's going to be a two-layer board. If it's just a single layer surface mount components, then I guess that could be considered a single layer. It gives us our dimension, the PCB quantity, how many we want. I think the least number is 5. The thickness, I'd keep it at 1.6 or 1.2. If you're doing some RF stuff that have some interesting headers, I go down to 1.8. Lets you pick the color. If you pick a different color, I think it changes the price sometimes. Oh yeah, no, it's 2 more days. That's it. Green, they can turn around in 24 hours. So print it really fast. Copper weight, whether you want gold fingers or not, in this case, no. Just keep the standard material. Pretty much keep everything here default. It's fine. And then you come over here and look, and because it's usually what happens if it's your first time using the thing, they give you a coupon. So for 5 PCBs, it's $2. And it gets cheaper the more you buy per unit. The one thing is that the shipping is a little costly for fast shipping. But here's the deal. If you take the amount of money that it's going to cost you to have 5, so it's going to cost you $2 to get 5 PCBs printed up, it is still cheaper to buy from them and get those circuit boards and have it fast delivered from China than it is in 2 to 4 business days than it is to get it from Osh Park. It is both still cheaper and still faster, even though it's coming from China. So it's just a really nice service, and I just started using it. It's beautiful. So that's wow, that was a windstorm. So that's kind of all I've got for you today. If you have questions, please throw them in the comments. I will entertain such things. Also, let me know in the comments if you would want some more of this. So for instance, if you want some KiCad stuff where we use like ICs, so any kind of like amplifier chips, or if you want to see like what it looks like. So I just got done with I was helping a buddy out. He made a badge for DEF CON. And it was just a really simple badge, but it was pretty much his company logo. It was like a wolf, and so we put like LEDs in the eyes for the wolf, and it was a really small kind of a badge thing, but it turned out pretty cool. I like it, and so I can show you how to like bring in a custom logo and put stuff around it, or so we can make a build a badge kind of workshop. I don't know. Or just put a more complex circuit. We could do that. So if you want some more KiCad, let me know in the comments there. If you have any requests for any sorts of live stream videos for the future, let me know as well. See what we can do. I hope this was of some value that you guys got out of it, and I hope that the PCB, the breadboard thing was helpful too, because I know some of you had some electronics before, but being able to pop back to the breadboard and play around with it and have, I put on the thing a wiring kit. So some of you might have brought the wiring kit. The wiring kit's really helpful in that this is all solid core wire, right? So it slides really easily into the breadboard, and I have had the same wiring kit since college. It's just been a wonderful thing. Don't build anything with the wires from your wiring kit. I'll only use them on the breadboard because they're good for that. hopefully of some value here. Yeah, so yeah, let me know of any questions you got. I'm gonna keep the stream open here for a little while for anybody to leave any comments or make any questions or whatever. And after about 5 or 10 minutes, I'll close it out. So cool, guys. Thanks for coming. If you are wanting to subscribe to the channel, I put up some videos occasionally. You can subscribe. Also, if you would like to, if you are U.S. government and you'd like to be on the newsletter so you understand when things like these are popping up or when classes are available and stuff, go to my website and register and use your government email address. That would help me out to be able to pick out who you are. Also, if, let's see, what else? If you have any suggestions, please leave them in the comments or get in contact with me. I'm on every social media platform there is. So, cool. So, yeah, you're welcome, Ralph. Good to see you in the comments again. Good to see everybody in the comments. Yeah, thanks. Thanks there, everybody. David, B. Will, Corgan. Sweet. Oh, Mr. Rollins. Good to see you in class, and I hope these are valuable to you. Yeah, like I said, let me know if you had any more ideas about what you'd like to see. But I'm going to keep the stream up for a little while. If you have any comments, just throw them in there, and I'll be around to answer them. All right, I'm just going to mute this mic.